So thank you so much for the invitation. Thank you so much for everyone to be here. Today we're going to talk about 3D landslide sensing and AI hazard classification. Before starting the presentation, what I want to say is I I am someone that is working in machine learning and AI. I have to admit that AI has been a trend the last years, but AI and machine learning has been here more than 20, 25 years. So we didn't have the computer power to run those models, which we have today. So it's not a tricky word. It's not so buzzy most of the time. So we have to understand what we're doing. Same with modeling, right? When we're using models, we should be able to understand what the models are. So it's not a matter of trend. So before going into the presentation, probably most of you you don't know me. So I wanted to give you a perspective of who I am. So my name is Stratis. My surname is Karantanellis, which is half Turkish because I'm coming from a place called Lesbos Island. Since I remember myself, I had many friends from Turkey. Unfortunately, I never learned Turkish, which was one of my things. However, I consider myself a global citizen because I was very active since I was a student. I wanted to go abroad. I wanted to learn more about how words is looking to our sense. So I'm coming from Lesbos Island or Mytilene. It's just opposite from Ayvalık, from those who are familiar, and this is the place that I was born. I studied in Thessaloniki, the second biggest city in Greece, up to the north, which is around here. And there is where I started looking what are my future. I love food, which is a very nice place to be in Turkey. And I consider myself an earth explorer because I want to travel all the time. So that's what I'm trying to do. The tricky thing is that I used to play professional basketball until 21 when I considered that professional basketball was not for me because I had an injury. So the second big passion was environmental and geological engineering, and that's how I started looking to that. This is me like 5 years ago, if you believe that. No, this is very small. This is my family. And one of the biggest quotes that I try to adapt to my students also is if you're doing something, doesn't matter what is that, but do it with excellence. And it's a great thing to consider. And my wife and my cat, because I'm a big cat lover, while my cat doesn't love me. So yeah. So that's good for who I am. And I think it's time to go and understand what we're going to talk about. So today you're going to listen I'm going to talk about three projects. They have a very similarity among each other, but at the same time, they have plenty of differences. And since I did my master's in ITC, I learned that when we were looking to some data sets, there are plenty of things that we don't consider because we have a very specific perspective of how things are based on our background, based on our studies, and based on our family. So what you're going to look today and what I'm going to show you, I want to keep your mind open and think outside of the box that you're used to. Because when you see things in a different way, you can also understand those things in a different perspective. A little bit about what you're going to see today. So, beginning, we're going to see why we're talking about Earth surface hazards, landslides, rockfalls. We're going to try to contextualize the problem and see what is the research background behind my research and my group research. Three different projects. We're going to see an object-based landslide analysis in Greece, in the beautiful island of Santorini. We're going to see how we try to estimate the volume after the landslides that happened after the Kaikoura earthquake in 2017, and also the multi-scale rock mass evaluation, because my background is in engineering geology. So what I'm aiming is trying to see how the different scales can correlate between each other. So we are talking about micro scale. We can do very nice experiments in the lab, but how we can correlate those results in regional scales. And what I'm going to end is what are the future directives on my work. So here are some collections about the hazards that the news are outlining. If you're able to understand, they're coming from different countries, different regions, different ethnicities, right? So hazards, and I'm talking about hazards, are related with disasters, but they are not natural disasters. There are hazards, natural hazards, that due to the overlap with the us, with humans, are transforming to disasters. So when I hear someone talking about natural disasters, I'm trying to consider why the disaster can become natural. It becomes natural because we as humans has an overlap with those hazards. And if you consider that we're not existing in this world, there would not be any disasters because there's no overlap with our living, with our everyday living. But let's say about the specific land surface hazards, right? And that's an example that I put it out from 2 years. So they happen different disasters around the world. And it's not only due to the earthquakes, we can have landslides, rockfalls, land surface hazards from multiple sources. You can see over here that we can have the sliding surface because we have erosion. We can have snow melting and we can have landslides. We can have a rockfall after an earthquake. So usually landslides, rockfalls, and land surface hazards are not documented as the rest of the hazards. And they're not documented because they're very abrupt changes most of the times. And if there is no house or there is no human being in the vicinity of those hazards, we're not able to document. However, the last years, we have several tools that we can use in order to monitor and assess those hazards. And those tools, most of them are related with remote sensing and GIS. It's not something new, but as I said, with AI and machine learning, this is technology that is easier for us today to use it. You can say that it's due to the computer power, is due to that it's not so costly as it was in the past. I remember myself when I was using in ITC and I was doing my master, I was using a drone, which it was not easy to use it. Today, everyone can buy a drone with 100 euros. So it's completely different, the adaptation that we have to those tools. The difficult part is how we can use those tools in order to assist us with our everyday life, with our everyday assessment. So some facts is in 2024, at least 12,000 people globally, 30% more than the previous year, lost their lives due to those hazards. There's no number how many people lost their lives, especially from landslides, but I can tell you that we have last year in US more than 1,000 people they lost their lives directly from a landslide or a rockfall. It's not documented anywhere. The number of deaths caused directly by landslides globally has increased almost 60%, which is a big number if you consider that a landslide is also considered a rock that is going to fall on our head, right? So it's completely different the perspective that we're looking to things when we're considering hazards. So this is a global land surface hazard maps. And when I'm talking about land surface, we're talking about landslides and rockfalls. And the pattern that you can see is mostly related with earthquakes, right? So we have red zones, which means red zones is a high hazard. But what is happening over here, right? There are landslides also there. The issue is that how we consider the hazard and how we can translate the hazard from itself to a risk. Again, once again, we're talking about people, where people are living. And if you go to this region, and this region is where I'm working, it's very red. It's very red because it's a very wealthy region. People that are very wealthy are living there. And because we have wealthy people, it means that they're building houses in very remote areas. They're building houses in areas that they know in advance that they have a high hazard of landslides. So high landslide hazard with the overlap of humans, it makes us to have high risk. So the same hazard, it can stay also for the area that you can see in green. And I can show you an example that we had a hurricane last year. Not so many people were living in Kentucky, but we had Hurricane Helene, and we have several people that they died. But the region is green. Let's go a little bit deeper to the area that I'm talking about, California. And this is an old map of California. This is a topographic map. It's schematic. You can see some events, some landslide events, the inventory map that is out from USGS in the area. And here you can see the map from landslide risk map from USGS. So this is the area with the county level. This is LA, right? So the whole area in LA, which is a plain area, most of the metropolitan city of LA is red. And it's red not because it has a high elevated topography. Because when we're talking about landslides, we're considering about topography, we're considering about elevated areas. We're considering like very steep slopes, but it's not only steep slopes. And we're going to see a very nice example from a coastal area that has one of the biggest problems regarding landslide. And let's say about this area. So these are several landslide events that happen in the wide area of Los Angeles the last 2 years. Different forms, different mechanisms of landslides. We're talking about rockfalls, we're talking about debris flows, and we're talking also about slow moving landslides. All of them are within the landslide hazard, but the mechanism and the way that they're creating issues are completely different. We're talking about a radius of more than 20 kilometers. And in a radius of around 20 kilometers, we have steep slopes, we have areas with very gentle slopes. Even that, we had several issues with landslides. And those are just some figures that you can understand what are the issues that came out. And let's go to see a little bit more of the research. So this is a red figure that shows some of the hazards and how they're projected in the future. Why I included that? I included that because you can see the green line that is exponential increased, and this is the land surface hazards. This is most of the landslides that are going to happen. Why do we see an increase to those hazards compared with geologic draft and meteorological? We know that there are going to be more extreme events, and that's the issue about having landslides. But the issue of this exponential increase is that most of all the other hazards except of landslides, the result is landslides and are not documented because we're starting documenting the landslide the last 20 years with several ways by using ourselves to go and monitor, by using remote sensing, by using satellite data, we're trying to monitor them. So we're able to understand where and where are those happening. Starting from micro scale, going to macro scale, from a neighborhood level, going to regional level and globally. We have the tools to do that. But the problem is how we can use optimally those tools in order to get better results. But when we're talking about landslides, I want to understand what is the environment, right? We have storms, we have meteorological events, extreme events that are producing those landslides. And there are different events that we can have landslides up to the mountain where people probably they're not living there, but the result of those landslides can be evident down to the floodplains, right? We can have different sense of how those environments are changing. And it's very critical to understand that the landslide that happens up to the mountain can create also several issues in the downward area. We can have down lakes, we can have several events that are constructed into the environment. The issue is how we can understand and how we can cope with those events, how we can assess and monitor those events in a better, accurate way and more efficient. Because now, as I told you, we have the tools. So we should try to understand how those tools can assist us to make them better and more predictable regarding ourselves. This is a pre-event picture of an earthquake that happened in Sichuan several years ago, and this is at the right is the result. So what you can see is we have several landslides, right? This is how the figure looks like. But what we should be able to understand is that we have several issues in the rivers. We have several issues in the environment as a whole, because the environment is not only the landslide, it's not only the slope, right? The environment, when we're talking about the environment, they have several spheres. We have the biosphere, we have the geosphere, we have the different environments that are playing a role. The issue is that how these cascading events are creating the problems to our society, and that's how we should be able to understand those issues. And in order to understand those issues, we have to understand what are the different components of those environments and the interaction between those different events, right? We have the weathering, we have different biochemical processes that are happening before the event, before having any landslide. And those geomorphic processes are playing a role to construct the environment in order to have the environment that we're going out and we're enjoying when we're going for hiking or trekking. Those processes are happening every day, and most of them are not obvious to our eyes, are not obvious to our environment. But when something is changing, it has to find a balance between what we had before and what happened after that. And in order to have this balance as humans, because we're talking in a geological time and the changes sometimes is a matter of seconds, is how those are scaling and how those are scaling between the different environments. So we talked about an environment that is uphill. We're talking about an environment that is up to the mountain, right? We have the deposition zone, but before the deposition zone, we have the source zone. But it plays a vital role if the deposition is 10 meters from the source zone, but it plays a vital role if this deposition zone is 2 kilometers away. Because if it's 2 kilometers away, several processes from what you can see here are playing a role of what is going to be the sediment. Because also myself, when I was in my PhD, I was trying to understand what is the different mechanism, what is the role of the different landslide mechanisms. But what we're trying to understand is how those different processes are playing a role in the properties, in the landslide properties. It plays a role of what is the specific properties of the rock. Do we have a rock? What kind of rock? Do we have a soil? Do we have interaction between the soil and the rock? Because it plays a role what's going to be the result. Usually, I'm considering myself also, we're looking to the result without considering what is the source. So we should be able to understand the different components of those systems in order to be able to have the proper assessment. And in order to have the proper assessment, we need those tools to do that. I will get you to this exciting, according to me, landslide. We're talking about La Conchita, California. This is a landslide that happened in 1995. We're talking about the Highway 1. This is one of the most well known roads in California and the whole US. And it's going from the southern part of the borders with Mexico up to the northern border with Canada. And this is just a little bit between Los Angeles and Santa Barbara. So this is a landslide that happened in 1995. And what you see here is the same landslide spot 10 years ago, 10 years after the event. So we had landslide 1995, same spot, same landslide spot 10 years after that. So either we were not able to understand what was the issue, or we didn't want to find the solution in order not to have the landslide. I will get you to the map. So what you see here is the result. The blue is the landslide in 1995, and the yellow one is the landslide that happened 10 years ago. Different mechanism, different landslides, same spot. What was the issue is that we were not able to identify the area of the landslide because we were not able to predict that the same spot, even if we had some remediation after the 1995 landslide, that it was not enough because we were considering that we're going to have the same landslide mechanism in the same area. So the measures based on what was the landslide in 1995 were very good. But we didn't have the same landslide mechanism. We have a different one. We have a more soily landslide. So we should be able to understand when we're talking about landslides and when we try to forecast with our models, which are very, very efficient today, not only what happened, but what can happen in the future. And that's the tricky part. because most of the times we're looking for landslides considering the weather conditions or the soil conditions, but we are not considering what's going to be the change in the environment the next 10 years. It's not only building houses in the top of the slope, it's also the weather conditions, it's also like the soil conditions. It's a system, and that's how we should think in the future. It has been mapped, but the news were not able to understand what we're talking about landslide mechanism. Because in the news, we know that landslide happened and the landslide happened again. So we should be able to understand first in order to identify and forecast. I use models in my everyday life. I am a big, have a big passion for modeling. But if we're not able to understand what the model output is and how it relates with our area, we're not able to assess the model. And that's a big thing. Let's go to a slow moving landslide. Here is LA, the whole LA. Here's one of the most wealth part, and the whole area is moving. It's moving the last 20 years. They know that. Most of the people that they bought a house there, which is more than 5 million each of the house, they knew that it was an area that is moving. And last year, like 2 years ago, we had like a very, very rainy season, and the landslide started moving. We're talking about a slow moving landslide, which creates several issues. And this is a map that the USGS created by using SAR data. So you can see the red area is moving more than 10 centimeters per week. 10 centimeters per week, if you consider it in a 10 years scale, it means that the whole area it will go down to the sea, which is not happening because there is more than 10 billions dollars that they have been invested there in order to stop the moving. Till today, we're trying several teams by using the USGS, several universities to try to understand what would be the specific and more effective way in order to mitigate the moving. It's not an easy thing. It's not only one part, it's not only one landslide. And when we're talking about slow moving landslides, it's not only the water that plays a role. We have several hazards that are overlapping in the area, but people knows about it. So when you're going to buy a house in an area like that, you should know what would be the hazard. Let's go a little bit further, right? So you have seen that we have an issue, we have a problem, right? And we have tools. We have computers, very effective and efficient computers today, and we have tools. And remote sensing is one of those tools. Different scales. We have drones, we have lidars, we have satellite data, but we have also planes that can run and we can have data. We have different ways to use this data. We have models, but it's and different data sets that can come out from those platforms. Let's see how we can use a different data set, right? So let's go to the landslide analysis by using remote sensing. Different scales, starting from terrestrial data, going to middle form data, but also satellite data. We can have video and photo interpretation. That's the first stage that you can use and the most simplistic way. We can do some landslide mapping, either by using models or by using manual detection. Rockfall analysis by using terrestrial laser scanners or drones on looking on the face of the slope, we can identify in centimeter level specific rocks. We can use the multiplication of that and we can do some hazard analysis. We can use our models in order to classify the specific spots. And by classifying the specific spots, we're able to understand what and where the hazard is happening. We can do some monitoring. We can have on-site measurements. We can have tools that they are restricting in this area and they can monitor every second what is happening. But also, what I want to point it out is that today, with the application of all those tools, we can have a 4D analysis, a dynamic analysis. And by saying the 4D is I'm including the time scale. When we're going to end this presentation, From the 3D that we started talking in the presentation title, now we're in the 4D, but in the end, we're going to end in the 5D. And the 5D is another dimension that you should consider when we're talking about landslides. Hurricane Helene, it happens 2 years ago, almost 2 years ago. It's a hurricane. It happens all the time in the US, but it plays a role where and when it's happening. So we had a very high amount of water in areas that they were not prepared for something like that. The area that happened is a green area in the map that I showed you in the beginning. So we didn't have a hazard, but the result was devastating. Why is that? Because we had very individual people that they were living in remote areas up to the mountain that most of the people they didn't know what to expect. So that's a big effort that in several universities in collaboration with UAGS we try to cope. And why we try to cope several authors is because we have the scientific actions. I want to collect data for myself because I want to publish papers, I want to do my research. But it's completely different with the civic actions because right after the event, people were not able to go out of their houses. Several houses were drowned in the water. So it's two different things, right? So we should be able to understand what is the research part and what is the civic part. And this is a nice example because you can see that there is an overlap between what we consider as research as mandatory and important and what the civic actions are actually. So this overlap creates this collaboration between the USGS, the Geological Society, and several universities, but also several public authorities. So this is very critical in order to understand, in order to come to the results. After almost 7 days, we were mapping almost 24 hours in order to be able to know where the emergency authorities should be pointed out. And we're talking about the civic actions. And this happened because we had the satellite data to do that, because we had the public authority had the money to be spent in order to fly those planes and collect lidar data, and for us to being able to help and create those maps. So collaboration is a very, very important thing, especially when we're talking about hazards and how we can assess those hazards in an efficient way. And in order to have this information, we publish this map, right? Which this map was published not for the people, because people after the event they didn't care to know where there is a landslide. But for FEMA and all the public authorities, this map was one of the most important things in order to direct their efforts and being able to identify when they should spend their resources. So that's enough, I think, for the intro, and I think it's time to go to some cases. And to some cases, I will start with the first case, which is in Santorini, Greece. This is one of the most touristic places in Greece. And if you have the chance to visit Greece, I would advise you to go there, not during the high touristic activity, July, August, because it's very, very expensive. What is the funny part? This is the island, and this is an old caldera. So what you see here is an old volcano, and this is an active volcano. And why is this an active volcano? Is because last year, within almost 1 week, we have more than 2,000 earthquakes that happened in the area. Not very big earthquakes, but when you have earthquake to very touristic places, you can understand that there is a problem. So all those red points that you can see are covering the island because we had several earthquakes that are happened due to submarine volcanoes, not the actual volcano. So we were working in this area. We were working from 2017, and we were collecting data from from the very specific spot by combining UAVs, very simplistic UAVs, but also with terrestrial laser scanner. So we were fusing data. And that's a part of my PhD because I was considering like how can we use, I'm an engineering geologist, I'm going to the field, I'm collecting data on site, but at the same time I'm a big fan of remote sensing. So I would say, like, how can I use all this data? How can I create a model that can take this knowledge that I consider as an engineering geologist, and how can I translate it to a hazard? So I was going every 6 months until today. We're collecting data every 6 months, and we were trying to find a way in order to provide this landslide analysis, how we can extract the results in a more efficient way. So let's say that we're talking about a volcanic material. So we should find very steep slopes. We should find a better way to create models. So we were flying in a multi-temporal way, and we were trying to have a cross correlation of those stripes, those UAV flies, in order to collect accurate data, but not accurate for every time. We want to have the same data, same way every time that we were flying. The tricky part is when we started with Phantom 3, and we ended up today using Matrix 350. So we're talking about completely different technologies throughout the time. So we should find a way in order to have the same data set over the same period in order to be able to compare it, right? When you compare something, you should compare apples with apples, not apples with oranges, right? You should be able to understand what are the differences between the different data sets that are coming out. So you should be able to adapt to those different data sets. So we're talking about data every 6 months, and I will give you an example of what is happening. We were collecting data with UAVs and LiDAR. We're using their models, and every 6 months, we have a comparison between the models. That's one layer of information, right? So we have the 3D data, which means that we were able to compare in a 3D space between the different multi-temporal epochs what is a change. That's good. I mean, we have 3D data, we have 3D results, we know what changed, and we know where is the change. But we're talking about the same result that you're looking here every 6 months from 2017. So we're saying, like, okay, that's a good thing, writing a paper, but how can we can understand why this is happening? Because the critical thing is to understand why this is happening. And the most important is to forecast what is going to happen based on what is the past, right? Because the past actually is the key for the future. If we are able to understand what is happening and why it's happening, we're able to critically assess what can happen. And if we know what can happen, we are able to cope with the results. And there, we had data, we had the results that we were talking, and my idea was to create a model. But models need to be able to understand before going to modeling. So what I knew is what are my datasets. Different datasets. We have datasets collected in the field. We had datasets that were came out from modeling. So we should be able to find a way to collect all the datasets, fuse the different datasets, and being able to assess. In order to do that, it's called a method that is called object-based analysis, object-image-based image analysis. I'm not sure if all of you are familiar with that, but I will give you an example of what it is. It's very similar to GIS and pixel-based solution, but now we're talking in an object level. Most of you are not able to understand what is this, right? So we're talking about pixels. It's a picture. It's some pixels that are creating an image. And I zoom a lot in order to give you this image, which is not understandable. I will zoom a little bit out. Are you able to understand that? No, right? Does anyone understand what is that? No. Let's zoom a little bit more. Now it's getting a little bit more familiar that I can see something with a pattern, probably like a building. But if I zoom a little bit more out, I can understand that this is a building and I have some people that are standing here. If I am using pixel-based solutions, I'm not able to collect all this information in different levels. But by using object-based image analysis, what I'm doing is I'm using all the scales and I'm creating objects. Because there is a building here that I classify as a building, and I have people that I can classify that are standing in the building and not a pixel. And there is a one human that is wearing white. And this is the story, how it started. So I'm not thinking in a pixel level, I'm thinking in an object level, because that's how our brain is thinking. We're not thinking in pixels. I'm looking right now to you, and I'm looking humans, that are sitting in a hall on specific positions. And this is the story, right? It's not you're not pixels. You're wearing different clothes with different colors, and that plays a role for you, for the whole, and for the presentation that we're standing here. And the object-based image analysis has two specific stages. The segmentation stage, in order to segment my dataset by using a very specific method called multi-resolution segmentation. And I'm not going into detail, but it's a very straightforward, right? And the second stage is the classification. How can I classify my objects? My objects that are constructed based on pixels. But I'm not classifying the pixel, classifying the object. I'm classifying yourself sitting on the position, sitting in the whole area right now. That's the big difference with pixel-based solution. And in my result, I use two different methods. One, which is a knowledge-based rule set, how my brain is thinking, so doing a manual classification, and also by using a machine learning, because I wanted to see how good the machine learners are. But before going to the result, we have to classify our dataset. And how you classify the dataset, right? This is the dataset. Most of the times, the dataset are unconstructed. It's very complex. So I have to start sorting the data. By sorting the data, I'm trying to classify the specific points. Right now, I have colors, I have Legos. So I'm putting the Legos on the specific color. And by using those specific colors in those specific segments, I'm trying to create a story because that's how we want to do. So I take this idea and I try to see how I can translate it to my area. So I have the ontologies, right? I have the classes, the ontos, which in terms of landslide, I have the source area, which in this case is the area that I have the hazard, the source of the hazard, and I have the depletion zone, the zone that my material is ending. But at the same time, I have different non-landslide ontologies that can be placed into the landslide, but also out of the landslide area. But it plays a very important role where those elements are. It's very different to have a crack into the landslide or outside of the landslide and explicit where those cracks are. It's different to have a crack of 5 centimeters next to the source area and different to have the same crack in the depletion zone. And that's what I tried to do. I created an hierarchical classification of my dataset in order to create my story, and from my story to being able to classify my dataset and give a meaning to my story. So, a little bit about the workflow, collected data, different datasets, not so complex, like everyone can follow, everyone can fly a drone, you can collect the data, you can use photogrammetry in order to create your data sets or by using different sensors. But the important thing is how you can take the knowledge and you can translate it to what you want. And the whole story starts if you have the correct classes. And if you have the correct classes, you should be able to understand as a geologist or based on your expertise, what is the meaning of this knowledge. And I'm getting back to my beginning of my presentation saying like we have to be able to understand by ourselves what is the output before getting to the output, right? We should be able to expect something and being able to understand that. Two different ways, the expert base, knowledge base. I did it by myself. I use the layers. I had the classes, so I tried to manually understand what is each class and where is this located. And I use several machine learners almost 10 years ago. So I used the KNN, the decision tree and random forest, and compared it with my expert knowledge. And what you can see based on the numbers, because this is just a number assessment, is that they're very, very close. The only limitation, which I trust on myself, not the models, is that it needs time. But if you consider also in order to use those machine learning algorithms, we need to have data, and in order to classify and use them, it's also time dependent, right? So when you're talking about machine learning and AI, you should consider also the time when you reach the time to train a model, right? It's very, very important. What it came out is indeed by using random forest was the best, the most optimized way to classify my data. But if I have the same case and in order to be transferable, I should be able to understand what is the meaning of those differences. So some takeaways from that is that we were able to fuse different datasets. And when I'm saying different datasets, I mean datasets that are collected from remote sensing, 3D analysis, but also being in the field. And I touched the rock, I did several tests on the rock, and I wanted to use this fusion in order to get me better results. But at the same time, I didn't classify topography in order to have the landslide hazard. I tried to use all the knowledge in order to contextualize this information, and I used that in the watershed level, but also in the hill slope level. And by saying that, I would go to a regional scale. So now we're going to New Zealand. This is a big earthquake that happened in 2017. So our idea was we have several hazards that are happening, and most of the times we do not have topography before the event. Or if we have some topography before the event, it's not exactly before the event. So our idea was how we can create topography because it's not cheap to fly a plane and collect LiDAR data. And if you have a hazard, you're not able to go back to the time and fly a plane, right? So we use imagery, we use satellite data from pre and post event, and we use an algorithm called set topography, which what it does is gets overlap satellite data and it tries to translate that to the same way as photogrammetry is working. So we have overlap imagery, and from overlap imagery, we're creating topography. We use that the same way as you have seen the previous models, and we try to register the models between each other. And we try to do a change detection. And in order to do the change detection, what we wanted to see is how close we are in order to calculate the volume. And the good thing with this study is that we had previous studies that they had a volume estimation, and we wanted to compare with the previous studies. So let's start by topography from imagery, right? So we have imagery, same way as photogrammetry, and we were using that, the overlap imagery, in order to create the topography. What is the tricky part is that we have the pre-event, the post-event, and we have the post-LiDAR. But if you pay a little bit of attention to here, we have several artifacts. And why we have several artifacts? Because when you're using satellite data, it's very dependent on the weather. And the area that you can see here is a cloud. We're not able to get out of the cloud, right? So there are limitations. There is not one solution fit for everything. And when we're using those kind of things, you should be able to understand what are the limitations in order to do that. So we used the pre-earthquake topographic data. We had a SETS model, but we had also LiDAR for both cases, pre and post. And we used a small area from the landslides that happened after the event in order to see how close we are with what are the previous volume estimations. We use two different ways. We try to register and align the data because when you're using those models, you have very many limitations except of the pre-data, but also to how you register and align the data in order to have a good result. It's not everything fits for all. So in order to register the data, we did several tests. We cropped the area in areas that we knew that it didn't change, but also in areas that changed. And what it came out, you can see also from the graph, we compared the different models. As you know, the LiDAR data is a lot more accurate compared with photogrammetry. But what we saw from the results is the scale, how dependent is the scale. It's very dependent because we're not talking about the centimeter level, right? We try to normalize our data sets in order to be very close with the sets data sets. And we saw that when we're using sets with sets data, we have a better result when we're comparing with the LiDAR data. And that's normal, right? When we're comparing apples with apples, it's a lot better by comparing apples with oranges. And the second thing was to do the change detection and calculate the volumes. So we used a very straightforward way. a little bit modified by using Cloud Compare, an open source tool, and we tried to take every level, every point, and compare it with the other point. What we came out after cleaning is we tried to modify because first of all, what we did is see where is the change. And we used a 3D vector in order to identify where is the change. Since we knew what is change and no change, we used the same area and we calculated the vertical vector. We know where is the change. We excluded all the area that we know that it will be an error or something that it didn't change, and we calculate the volume only to the area that it changed. And we were able to segment and classify those areas. And we feed a model with those changes and see on very specific area, and we try to see how good it will predict the rest of the areas. Some very limitations is that usually when we're trying to do the same way, we're calculating the whole landslide area. By using the change no change and taking only the change area, you're able to identify what areas change only with loss area. So where are the regions that lost material and where this material went? At the same time, we use an exclusion because as we're talking about regional scales, we had to be able to identify some superficial change. We had trees. And because we were using photogrammetry, we were not able to exclude those trees. So we used a very specific exclusion part, which is a point 3 that you can see regarding the portion of volume to area. And also we were able to see what is the volume displacement, and we were able to reach also 15 square meters, which is a very good result if you're getting the data with 2-meter resolution. So as this figure says, we were able to identify where is the loss area and where is the gain area. We were not calculating the whole landslide area. We defined where is the landslide. And by doing that, we went to the normal case. So we were trying to calculate what is the volume area. And we compare it with several studies that happen in the area. And we were very, very close by using a very non-costly method. We didn't use any LiDAR. We didn't fly our LiDAR planes, but we used data after several years in order to validate what we were able to see. That. Some takeaways of that is the scalability of the method. You can do that for the whole world globally if there are computers that can run and if we have the models. The availability of the pre-event topography, because we're talking about the most important thing when we're talking about landslide is the topography. And usually we do not have this data set. But also the 4D analysis of the geomorphological processes. Because we're, as I said in the beginning, we're talking about an environment. And we should be able to understand the environment before assessing the event, the result of that. Last is the case in Puerto Rico. For those who are not familiar, Puerto Rico is a US territory. They're not able to vote for that, but they consider it as a US territory. So Puerto Rico is in Caribbean. There are several hurricanes that happened in the last 10 years and earthquake events that created several landslides. And one of those, I was quite lucky because I was in US the last 5 years. So I was able to go to those 2 hurricane events that happened and being able to collect data and understand what are the individual simplicities in this area. So we went to the field twice in 2022 and we used several satellite and LiDAR datasets that are existing, but we collected also our dataset. And the idea is by collecting engineering geological properties of the rock, going to the field, doing different tests, to being able to understand how we can cope with those models, how we can cope with those events. So we collected site-specific. We went over 200 cases, and we collected with the Smith hammer the specific rock properties. We tried to use assessment tool. In this case, what you're looking to is a GSI tool. So every time that we were collecting some specific rock strength properties, we were trying also to correlate that with the geomorphological processes in the area by using the GSI. And we did it for several areas within the island of Puerto Rico. So we used Smith hammer harness, and you can see starting from the centimeter scale. So we used several tools, but we used also satellite data. And as I told you, we had two hurricanes and one earthquake event. So we collected the data sets from those events and correlate with what we came out from our result. So we had a 6.4 earthquake that happened in 2020 and two hurricanes, Hurricane Fiona in 2022 and Hurricane Maria in 2017. Hurricane and hurricane, the red points are landslides. 2017, 2022. We have more than 60,000 landslides that happened after the hurricane 2017, and we had around 200 landslides that happened after 2022. And we say, like, how it's possible? Like, we had even highest precipitation of rainfall that happened in 2022, but we have less landslides. And we were trying to understand why, when you have a high precipitation event, you have less landslides compared with an event that has less precipitation. And that's the tricky part. So we try to collect data and we're starting to analyze the data. So what you see here is Hurricane Maria. Hurricane Maria is the event that you saw with almost 60,000 landslides. And what we did, we took some results from previous cases, from previous studies, and we tried to analyze it and see why this happened in 2017 and not in 2022. And we tried to adapt some rainfall thresholds, very simplistic method, but our goal was to try to understand why we didn't have landslides. Because when you look into those specific events, you're getting 1 + 1 = 2, but it's not like that. You should look to the history. You should look to the past in order to identify and understand what happened. You should be able to understand what happened in the past, right? So in the end, what you see is that we had with very simplistic models, and by using the frequency ratio, we came out on the landslide event results. But we didn't consider the environment, right? Because 5 years ago, we had a very, very high landslide event after Hurricane Maria. So the environment had already failed because all the material that they were standing in a critical state with a factor of safety almost 1 failed. So there was not a time to adapt after 5 years in order to have more landslide. Which, in simplistic words, it means that everything that it could fail, it failed. So in the next stage, we didn't have the capacity to have more landslides. And that's what it came out from that. Because we had 2017 Hurricane Maria, we had an earthquake, which is a very locality, because the earthquake landslides mostly are around the area of earthquake epicenter. But the hurricane happened to the whole area. So the capacity was not evident of having more landslides. This is some results from the frequency. So what we're trying to see is we try to analyze specific rock mass structures. And what it came out is that limestones and in general the sedimentary rock were easier to fail. And easier to fail because we had high weathering. We're talking about an area that has a very high weathering degree and plays a vital role of what landslides are we considering. Because 95% of the landslides that happen in the area are superficial changes in the layer between the soil and the rock itself. So the surface of the rock that is weathered, it fails in these cases due to the weathering. And we tried to see how the correlation between the elevation and the slope compared with the earthquake that happened plays a role on those specific rock masses. And even that, what you see in the bottom is the different limestone units. So we went even one step deeper to our rock masses and we tried to understand what those specific limestone units, those sedimentary rocks, are failing. So we did the testing, we did the correlation with the rock mass properties, and we try to visualize that compared with elevation and the slope. So what we you see here is the red zone was excluded because we're talking about very gentle slopes and not so elevated slopes. So we try to see what are the extremes. But what are the extremes? It's not the normal case. And that's how it came out by using those graphs. Because what we were expecting here is the red, which is the Juana Diaz formation, the Juana Diaz limestone, to be the higher. But compared to being higher, what we saw is the Ponce, which has the less landslide, have the high severity for failure. So we produced different maps and we were trying to understand how we can model also the slope stability of those rock masses. So what we did is that we did a back analysis of the landslides. We tried to, first of all, segment our slope, our topography, and we use a very simplistic way in order to calculate the factor of safety. So from micro scale, from centimeter level, we're trying to push it to the regional level. So we were collecting data to the microscale and we were trying to extrapolate the results by using interpolation of the cases that we were collecting on the slope level. And we use the Kalman method, which the Kalman method is a way to do the back analysis based on the factor of safety. So what is failing? And if my factor of safety is falling less than one, what is going to fail? So what we you can take out of that is by integrating multi-scale field and remote sensing can give you very nice rock mass evaluation results. It doesn't mean that it's always realistic, but what we're trying to aim here is to have the first post-resonance idea of what happened to our environment. Because if you have an initial idea of what happened, you're able to direct your studies after the event in order to be very explicit to what areas are you going to analyze. And those tools are that we use is to see how we can link the microscale with the macroscale, which is very, very important if you want to do some post-resonance analysis. By saying that, we talked a lot about landslides, right? We talk about rainfall, about earthquakes, about climate change, which climate change is a forbidden word to my case. But we're talking about hazard itself, right? And if we consider like this cross correlation of Earth's surface processes with the geospatial technology that we're using, we know that we have the tools today to create very nice digital models. We can include all the knowledge, the topography, the color, the different levels of information. But we're still, most of the times, we're missing something very critical, and that's my idea for the future is that we need to create those models that are intelligent. And intelligent, it doesn't mean that it has to be artificial intelligence. Intelligent means that our brain is seeking intelligence in several ways. And what we should think about is how we can transfer the way that we're thinking, our perspective about landslide, about climate change, about failures to a model, which is not an easy way to do that. But we should start thinking towards that, which is, again, it's applicable, but not easy to have. And by ending this presentation, I want to point out those three pillars that I started thinking after my master 12, 15 years ago. We're talking about those surface hazards. We should also consider the extent. It's different to talk about the micro scale. It's completely different to talk about the regional scale, but we're talking about the same properties. The rock properties don't change with extent, but there is a diversity between those properties, and we should always consider. Same with the field investigation. When we're collecting data, most of the time it's site-specific data. But when we have a sedimentary rock or a limestone, it's a limestone or a sedimentary rock. It has some similarities. And we should be able to understand those similarities, but also those differences between those rocks. And the last but not least is the remote sensing and geospatial technology. Those are tools, and we should be able to identify what are the capabilities and also, more important, what are the limitations. Because if we are aware of the advantages and limitations of those tools, we're able also to assess the result of those models. And by saying that, I would like to thank you so much for your time and sorry for taking more time for that.